Hello everyone, I'm happy to see all of you today, and I believe this time we have like a bit more people than last time, and this makes me really happy. And even it's raining. So today I'll talk about solution and maybe some ideas that were behind this solution for the problem about like Kaggle Carvana image segmentation. So my name is Vladimir, I'm data scientist at Lyft. I have PhD in physics, and currently I believe in global Kaggle rating. If you look at the like leaderboard or whatever it's named, ranking, I'm somewhere like 31st or like top 50, like in this place, yeah? So early in the days when I started Kaggle, it like looked like unreachable, something like this, but I mean, right now it looks very straightforward to get there, and yeah. Okay, so let's start. So what is the problem? In some sense, like I really like working with computer vision problem because you don't really need like to spend a lot of time explaining what you need to do. You don't need to explain how this like credit card risk planned on something. Just basically you show pictures, you say this is your input, this is your output, and that's what like you need to create a model that consumes things that you have on the left and outputs things that you have on the right. What does it mean? So on the left you have some kind of image of the car on some more or less fixed environment. So background is changing between different images in this data set, but not really drastically. And yeah, as an output, you need to find like for every pixel, you need to predict like a label. Is it like car or not? And I don't really know why they do it, but I mean, I'm assuming they do these images, they just extract cars from this and then paint them in some other background, and this helps them in their car selling business. Okay, but from my perspective, it looked like this. And first I looked at this picture similar, I believe somewhere about 10 days before the deadline of this problem. Yeah. In general, like there's like numbers 735 at the bottom. Overall, after like Kaggle kicked all cheaters and like other like teams, there was like 735 teams at the leaderboard, and we finished first. To be honest, I need to say that like our score is better than guy in the second place by something like 2 pixels per image. And every image has like, 2.5 million pixels. So like roughly speaking, it's named luck. Yeah. I would like to know what was his solution for this problem, because our was like straightforward but complex. But yeah, he didn't share it yet. Hopefully he will do it in future. Okay, so like typically when you have like machine learning problems supervised, you have like train test split and like what was happening in this problem. So in the train set we have 5,000 images. Test set was split into 3 parts. Public part, it's like public test, like 1,200 images, and when you train model on the train set, then you predict on the test. Public leaderboard shows you scoring and your ranking with respect to this like 1,200 images. Yeah. After competition is over, it shows you like accuracy of your model with respect to like another like 3,600 images. Yeah, and this is used for final scoring. For example, on the public test, on the public leaderboard, we were second, and after private set was released, we became first. So yeah, there's like moves here and there, and some like people had more like drastic moves. Another thing, and I'll talk about this, that was like also in this data set. Overall, we had, I believe, like 100,000 of images in the test set. So labeled were only like 1,200 plus 3,600, and another 95,000 were added just for fun, for popcorn, and like to prevent people from like hand labeling. Of course, I mean, like there is money and you want to win, so of course a lot of people, they have intentions to cheat. And one approach will be to beg and ask people, please don't cheat, please do what we want, and please follow our rules. Another like more reliable approach to create some kind of environment that will automatically prevent people from hand labeling, from some other kind of cheating. And it's widely used these days in these competitions when people add like a lot of just unlabeled data. In this set, it was like 95,000 images. And later on, I'll tell you like how we took advantage of this. Yeah. Every car was represented in 16 different fixed orientations. So like this Carvana like company, when they were doing these pictures, 16 fixed orientations. We did some attempts to exploit this fact and create separate models for different angles and like do some other tricks, but overall nothing worked. So for like all future like discussion, we treated these images like in the same way. Yeah. So of course, like if you have some kind of competition and you have some kind of leaderboard evaluation, you need score, some one number that will tell how good your model is. Typically for models of like binary segmentation, like two metrics are used, either intersection of a union, also used as Jacquard, or dice score. And they all kind of like both kind of similar, and overall they want, it's like a ratio of the overlap, your prediction and ground truth. And in this sense, I'll just like show it like this on the like bottom left corner as metric. Y, let's say it's your label, and P your prediction. So intersection divided by the sum multiplied by 2. So dice is varying from 0 to 1, and intuitively, like one can think about this like similar to like accuracy or probability or whatever you want in your head, like some number going from 0 to 1, when 1 is perfect, 0 is like horrible. In the middle, it depends. Yeah. Actually, okay, next slide. Nothing to tell here. Of course, like, every time you work with the data, you have issues with the data. And typically, I mean, at least for me at work, I spend like, I don't know, about 90% of the time, but 70% of the time dealing with mistakes, inconsistencies, and some other issues with the data that were just like absorbed from like some kind of environment. And here it was also the case. Yeah, there were some mistakes in masks, and like on the left, you see example of this, something like near the like left mirror. One of the biggest problems that like people met in this like competition was like on the like top right corner, you see like two like nearly the same like profiles of the cars, and one of them have some kind of like holes in the like wheels, yeah, and another does not. Which of them is correct? I don't know. It depends on your task technically when you do some kind of data science deep learning model. But in this sense, like people, they were marking these like masks like in this like Carvana company, they were not instructed how to do it, I believe, and like randomly in half cases they like labeled these holes, and half they did not. And this was like in train set, and it was also in the test set. So I mean, this added some noise to our model, and this also added some noise to the evaluation. So I believe if it will be either holes in all of them or like holes will kind of like filled in all of them, you would have like, better like score and slightly better models. Yeah. Typically, let's say if we are working with some kind of like some other data science like problem, let's say this like holes, yeah, sure, it's a mistake, but it's not really a big deal. It's just like few pixels and things like this. But for this data set, which was overall, even like considering and taking into account all these mistakes, was extremely clean, extremely nice, and there were no problems with validation. So overall, this data set was like an exception from typical Kaggle business when you have like data leaks, noise in the data, validation doesn't work, train set and everything, train and test come from different distributions. It wasn't the case here. So here it was really, really nice. And from time to time, people like message me and ask like maybe like we are trying to work on some paper that I published about like, segmentation, maybe something else, and we are struggling here and there. Recently, I started forwarding these people to this competition and say, here's clean data set, here's like clean problem, just like try to train model, and even now after competition is over, you can submit your predictions, your model, and like leaderboard will show you how good you are with respect to the people who like work on this problem. And that's what I tell to these people. You get to the like, let's say top 10%, and after this you can like, go for other like binary segmentation problems, and you will not have that many, you will have a lot of problems, but they will be like not about networks, but more about working with the data. So in this sense, like if you are thinking about which data set to play with to get better understanding and practice, how can I understand if I'm good or bad, maybe, typically when you work on some data set, you don't know. Let's say you get like 0.8 score of intersection of a union. Is it good? Is it bad? Who knows? And this leaderboard will tell you like how good you are with respect to like, 700 teams. Yeah. So if you're thinking about this, also you can do it. There are also some tricky cases. For example, you see this like on the bottom right corner. It's good example of the, so it's like some example from the test set. And you see this like white van on the white background, and on the right, predictions that our network was doing like from scratch. And as you can see, there's like some mistakes there. And instead of predicting a van, it's trying to predict it as a truck. And yeah, mistakes about this. So main reason is that there was like no vans in the train set, and of course none of them were like really wide. So basically it's just like some tricky cases that we at the end like use some heuristics, some post-processing to like take care of. Yeah? Okay, so what was happening 10 days before the end? Problem looks extremely boring. No one wants to do it because I mean it's too boring. So but just for sanity, because data set is clean, because everyone has like pipelines about binary segmentation, you just like need to change, input for like input output, train your network, do predictions just for sanity. And so Alexander and Artyom, they like did this thing, and they got like, I believe, after a couple submissions into the top 5, then they merged their efforts and they got to the 2nd place at the time of the competition, yeah? I followed similar path. I just didn't want to do it at all because, I mean, not that much knowledge from many perspectives. There were like other interesting problems happening at the time. But again, I trained some model and I got 5th. And at this point, you know, you're starting feeling taste of money. Because, you know, like money is given for first 3 places, and you know, you're 5th, and you just like, and your friends are like 2nd, and they're like telling you just like, let's merge together. Do you want like, you know, to play this game? And at this moment, this problem is still like not very exciting for you because, I mean, segmentation is segmentation, but this taste of money adds some flavor to it, yeah? So yeah, we merged into the team, and then like we got like 2nd, and then we added, improved, and overcame all efforts of our competitors because like they improved our score, we improved our score, and we finally ended like 1st. In terms of background, so all of us are Kaggle masters, all of us are at top 100, and I mean, so Alexander and I are using deep learning aggressively at work, so in this sense there's overlap. Competitions help at work, and like, you know, some experience that you get at work and this deployment, the industry type environment, it helps in the competition. And Artyom, he's a graduate student in Heidelberg University. As I remember, he has some papers at NIPS, CVPR, so like right now he's deep into this like, you know, research type problems, yeah? But still, I mean, and there was some blog post that he wrote at some point in Russian about how Kaggle helped him to publish 2 more papers and why, like, and what, things like this. So in this sense, yeah, for all of us, it kind of like helps, yeah? Okay, so what the approach did we use? The best baseline that we know right now about binary image segmentation is UNet. What is UNet? So here I show you 2 examples. So if you take architecture of encoder decoder, something that you use like in autoencoders, yeah, you add skip connections, you add UNet, that's it. Basically, and some guy who like, you know, got this idea about this adding the skip connections, he published this paper, instantly he was invited to DeepMind, and I believe that's where he's like, you know, doing like some science research right now, yeah. It can be like separate discussion, why, what came, like, you know, what was the motivation between this and what were some brilliant ideas, but like from practical point of view, if you have binary image segmentation, you have this deep hammer. Basically, you take some data sets of your labeled binary mask, and it may be not necessarily big, like typically to get some decent result, you don't need 5,000, you don't need 1,000, you don't even need 100. Like, I mean, apply it to 50 and we'll see what it will like, you know, what will happen. It's good enough, yeah? So UNet is really great baseline, yeah?
Can you explain UNet in a little more detail, please?
I mean, sure, like what is UNet architecture? UNet architecture became as an improvement over SegNet architecture. And SegNet architecture was basically merging ideas from FCN8 and autoencoder. Beautiful words. What do you need like to know as a practitioner? If you talk about some kind of classification problem, and like how does network for classification typically look? Some layer of convolutional layers, and then like max pooling, and like with every like block of these like layers, you get you decrease size of your convolutional layer, and you get like more filters in each of them. So basically you get this type of pyramid. And that's what you may observe. Let's say if you look on the picture on the right, this like left side of it, you see like, you know, thin but long layers. They like change to like something like shorter but thicker. And this is typically like, you know, type of the like any classification network like ResNet, VGG, like Inception, whatever you want. And that's like what is responsible for feature extraction. Yeah. And this is left part of the network. So what was proposed on the architecture SegNet, let's mirror it in some sense. And so in the middle, you see that like, you know, like really short and thin blocks of convolutional layers. So now you can go to the right and try to do some kind of deconvolution or upsampling procedure. Again, shifting deconvolutional layers with convolutional layers, and then like it becomes like thinner and like longer, yeah? Until it gets to the same size as it like initial input. And this would be SegNet architecture. Then you can add skip connections as shown here, and you get like UNet, yeah? UNet is so good as a baseline, and it's so extremely popular that in the field when you have small amount of images, and right now I mean medical imaging, so they have really small data sets, they have binary segmentation because, you know, from business point of view and from scientific point of view, it's important to identify like, you know, positions, locations of some tumors or whatever they have. And yeah, it's very important there. So these days, if you come to some medical imaging conference like MICAI or like ECR or something like this, every other paper will be about we are not like everyone else, we are state of the art, we took UNet, tweaked it a bit, and we applied it to a data set that no one applied before, and that's why we are the best. And you literally will hear hundreds of this type of the papers. And I'm not kidding right now, because I observed it like in September at the MICAI, just because, I mean, it's really good like baseline. And I'm saying that like UNet, this like, you know, if you look at the right, there's like some numbers like layers, thickness, number of filters. It's not really that important. I mean, it's important for some particular task, but overall, when I talk about UNet right now, I talk more about framework. You have decoder, you have encoder, you have skip connections, and there are a lot of details here and there, but they like can be tweaked, modified, and there's a lot of research in this area, although not really like obvious to me how important it is, yeah? Okay, so, and that's what we actually did. And when I was giving a talk in H2O in August, I believe, about like getting 5th place and some money in some medical imaging competition, I used UNet. And I was talking about how good it is, and now I'm doing the same. In like May, when I was talking about getting 3rd place and with my friend, and we won like 3rd place out of 400 in some satellite imaging competition, 20,000 prize. I was talking about UNet, a bit different modification, but like, I mean, we got money with this. It's really good baseline. I'm not saying it's the best solution, but as a baseline, just way to go, and for many like purposes, it can solve your problem and you can switch to the next like task, yeah? And yeah, if you want cheap paper, find a data set for which it requires binary segmentation, look for literature that no one applied it, apply UNet, and you can publish paper. We're not like everyone else, we are state of the art. Okay, next slide. Again, probably I should tell all these like words here, but so yeah, UNet is really strong baseline, so that's what it can do on the top, like find background, and it's similar to this like finding cars in this Carvana competition to what we did, and it does it really on the pixel accuracy. Bottom right are data from the Konica Minolta competition that I was giving a talk, like I believe like in September or in August, and it's like again binary. UNet worked really well, different modification, but still. And on the like bottom left, I aerial imagery, finding like buildings there. So recently, few weeks ago, maybe a couple of weeks ago, finished not on Kaggle but on top quarter competition Urban 3D, in which from like some satellite images you need to find like buildings. And Alexander Buslaev, who was my teammate in this competition, he finished first. I don't know what did he do, but I'm suspecting that it was some kind of modification of UNet that was adjusted to this type of the data set. Yeah? My approach. Overall, what I need to know. We never met each other in person. Me, Alexander, and Tom, we met each other in person. I know how they look based on the pictures on LinkedIn or something like this. So how did we meet each other? We are all members of like Russian-speaking data science community. ODS.ai, we have like 9,000 people there, like aggressive discussions, top like, 15% of Kaggle top 100 are there and all things like this, simplifies things a lot. And basically we merged like because we knew each other from this like virtual like discussions. Yeah. Another question that I want to mention is how do people form teams? Often, you can see in some like forums, maybe at Kaggle, maybe at some like other forums, like someone is saying, I'm so excited about Kaggle, I never tried, but let's form a team and do like our best, like because we're excited about this. This approach doesn't work. The best working approach, there's a line type of the forum, like posts. I want like to master Kaggle and get more experience with this. Is there any mentor and I can pay money that will help me to get like better? I mean, just like to win competitions. This approach also doesn't work. I mean, I didn't try, but I'm guessing, yeah? Approach that works in terms of like, forming a team. And this is the only working approach that I've seen so far. So typically people work independently on the problem. Each of them has pipeline. Each of them has their own ideas, issues, like some tricks, tips, things like this. Somewhere close to the end, people look around at the leaderboard and they see who is near them, yeah? And then like these people that are near each other at the leaderboard, they form a team. Then they can average their like predictions, or maybe they can like make more complex solutions, or maybe they can share ideas or something like this. And this allows them, let's say, so as it was for us, like, second and fifth, or maybe like people like a bit lower. So roughly speaking, team at Kaggle is formed between people that are at the similar positions at the leaderboard. And this is the only working approach that I know. So situations where I'm excited about this problem, like, let's form a team and we'll win, it's just kindergarten. Show your high style, implement a pipeline, struggle with the data, understand its issues, and then it will be some kind of productive discussion with you as a team member. And again, it's like the same for me. I mean, yeah, I have some like experience in some other problems, but for any new competition, I would, like no one should ask me like to merge in a team unless I do something. So do something, prove yourself in this particular problem, and then ask for like teammates, or maybe teammates will look for you, which like typically happens. Okay, so about my approach. So when I was like talking about this like UNet type architectures in spring and like in August, it was just basically encoder, decor, and it worked well. When I came with this approach and I had like good pipeline because I showed good results in other problems, I tried it here and I was somewhere in the bottom 30%. All my brilliant ideas and all this stuff like that like helped me like to win other competitions here were like somehow baseline. Reason for this is that because I'm not the only one who's participating and I'm not the only one who's learning. So typically you have 700 teams and one competition. Competition is over, people discuss solution, and top solution in this like problem becomes baseline for the next one. Then you repeat this 10 times, and if you're not following like these things, all these tricks, tips, modifications, and some other improvements, you will just be behind. So what was my problem? Why my solution was in the bottom 40% and like for other many people they were like much higher? Trick is that for this problem, what really like helped is to replace encoder from just like encoder to replace it by VGG11 network trained on the ImageNet. Of course, it sounds familiar to you, like you take like pre-trained network, you apply it, and this great works well, yeah? Why didn't I do it earlier? First of all, because UNet works well even without pre-trained encoder. And second, because pre-trained didn't work when you apply it to like satellite images or some other like images. I'll talk about this a bit later. So overall, my solution, I had 5 folds. I was using full resolution image for segmentation, typically like downscaling or like shift or like some other transformations, they decrease performance. I use like augmentations in the HSV space. So I mean like often when you play with images and you try to do augmentations, you do some shifts in the color or like contrast or things like this, yeah? So what showed better results, and you can see this on the right, to take some image, convert it from AGB to HSV space, shift it there, then convert it back, and you get something that is like very similar to this original images, like, similar distributions. And after this, I and like some other guys, instead of like shifting colors forth and back, people starting playing in NHSV space, and typically it shows better results for us. Another trick that, of course there is paper about this, about like not everyone else and all these things. People use cyclic learning rate. What is cyclic learning rate? So like normal schedule with training network is you have some kind of learning rate, I don't know, like 001. Then you train a network, then you look for validation loss, and when it's got to the plateau, you decrease learning rate like twice or 10 times or something like this, and then it helps your network to converge further, and then you repeat this like one more time, and then you get like completely to plateau. Your learning rate is like 10 power minus 6, and you're good, yeah. And this works really well, but one can do better, and to win Kaggle competition, you need to do better. So what's happening when you when you decrease your learning rate, then decrease it again, and you go to the plateau, you get to some kind of local minimum. Local minimum is not a problem as long as it's like close to global minimum. But what if there's like another local minimum nearby that's a bit deeper, that can like get you better result? And of course, there is always like local minimum like this. Trick that helps. So what is cyclic learning rate? You have learning rate, you like go with, then you decrease it even more, and then you increase it again. And then decrease, then you will repeat this procedure a couple times. There are like few schedules about playing with learning rate, but what I'm trying to say, monotonically decreasing learning rate is not always good. It prevents you from exploring like nearby local minimums. And this is a straightforward way to get a bit more to the accuracy of your, I believe, any neural network model, segmentation, classification, detection, whatever you want. So cyclic learning rate, I believe everyone should implement as a part of their pipeline because it definitely works. Optimizer. Optimizer is a tricky business. For segmentation, in my experience and experience of my friends, Adam and RMS Prop work the best. For classification, I would still prefer like, good old-fashioned stochastic gradient descent. It converges slower, but overall like shows better performance. Probably because Atom is overfitting, or maybe because implementation of Atom is not that good. And there was like paper in NIPS about this. But like, it's all technical details. Overall, like for me, Atom I use for segmentation, and like stochastic gradient descent for classification. Batch size, I had 4. Why 4? Because people talk about, batch size should be, 128 to 56, something like this. I don't have enough hardware for this. I have at home like 4G, like in my computer, like I have 2 computers at home, one with 2 Titans Pascal X for for prototyping, like developing, and one dev box with 4 GTX 1080 Ti, and I'll show later on picture about this, of this device, that I use for training. Each GTX 1080 Ti has like 11 gigabytes of RAM. And it looks like a lot, but if you work with high resolution images, and you have such a memory heavy encoders like VGG. So for me, basically, in this UNet with pre-trained VGG 11 architecture, I was able to fit only 1 image per GPU. So this one image was eating all 11 GB of RAM. And that's why I had 4 GPUs, and I had batch was equal to 4. And this was actually mainly the reason why I use VGG 11 and not 16 or 19, plainly because if VGG 11 barely fit in my RAM, there's no hope for this. Either I needed to downscale the image or work on crops, which is also possible, but still, one of the ways. Loss. When you talk about, let's say, binary classification, what loss do you use? Typically, loss do you use binary cross entropy. Yeah? That helps you to distinguish. One may think about binary classification as about a lot of classification. So for each pixel, you have more or less independent classifier. They're not really independent, but still a bunch of classifiers for each pixel. And so you can basically treat them as classifier of binary, use binary cross entropy, and repeat this for all. And in this sense, if you have on the input 2000 by 1000 image, you will have how many? 2 million classifiers for each image, yeah? For each you apply binary cross entropy, you get some result, and this definitely works, and that's what is widely used in literature. On competitions, it's not good enough. What is the problem? Binary cross entropy predicts your probability of the correct answer, and for many use cases, let's say in business, so for credit scoring or some other problems, it's good enough. Here, your metric you want as a output mask, and mask means zeros and ones, not 0.5, not 0.7, not 0.1, zeros and ones. This should be a mask. And this means that after you predict probabilities for every pixel, you need to somehow binarize it, you need to threshold. You can do it with some fixed threshold, you can do it with more complex way, but it adds more complications into your pipeline, and if you can avoid this. So what is the trick? How you can modify it? Our evaluation metric is dice. So what works, you can make generalization of the dice that is can be applied to float predictions and add this to your loss function. So your loss function will at the same time try to optimize binary cross entropy per pixel and optimize your evaluation metric directly. Yeah? So we want to see dice, that's why let's optimize dice. It looks very straightforward, but if you look at the literature, it's not that widely used as it can be. What is the effect of this? And this enforces your network, this is a separate discussion why it's happening, to push your predictions to zeros and ones. Your network becomes confident or typically overconfident. Yeah? So it pushes towards 0 and 1, and this makes it's not that important, what threshold will you use? 0.3, 0.5, 0.7. If you just use binary cross entropy, it will be a problem how to choose your threshold. You need validation set, and there's a lot of pain and magic after this. But instant you add similar term, maybe soft dice or soft jacquard to your loss function and directly optimize for this threshold, and just pick 0.5 or 0.3 or 0.7, you're good enough, nearly the same. And this kind of nice trick and hack that again may be used for some other tasks. Yeah. On the 7th, I have pseudo labeling. What is pseudo labeling? I'll talk about this a bit later. Maybe it's next slide. No, not yet. So, okay, I was talking about does really pre-trained encoder helps your UNet models? And this is a good question. So, me and my friend Alexei Shvets, we took this network from Carvana and we run this in different regimes through some extra data sets. Actually, it was this IRL buildings. Yeah, we tried something that the features should be different. And what was the conclusion? Main point of the paper that preprint that we submitted to archive is that this image. So we just kind of expected behavior. Yeah? If you use pre-trained encore or like in general pre-trained network, it converges faster. If not, it is converges slower, but again, I believe they will go to the same value at some point. Question?
What's the difference between VGG11 and Carvana?
So what did we do? Let's say you have this Unit 11 architecture. Yeah? You can do it like this, initialize it with whatever, like Likun uniform or whatever PyTorch is like trying to initialize ways by default. You run this for 100 epochs on this data set, and this is your like bottom curve, yeah? Then you can, okay, let's do it like this. Let's initialize Encore with the VGG11 trained on ImageNet, and rest of this like Likun uniform or whatever is in PyTorch. And then you run it, yeah? And this is like one of the curves, yeah? And then let's say third like environment, we took weights from this problem that I'm talking about right now, trained for this prediction, this like cars. So in some sense, like both Encore and Decore, they're pre-trained on some other data set, in the sense as Carvana, yeah? And ran this again on this aerial imagery. So yeah, like they kind of show same result. Yeah?
So it seems it doesn't matter what you're pre-training your encoder on, like it doesn't have to be generic or even related data set.
I mean, yes, this is true. So yeah, there are like some beliefs, and typically it's the case that if, let's say, you want to do some kind of network on distinguishing dogs from cats, it would be really nice if you like have network that was pre-trained on some kind of maybe humans, maybe like buildings, but something that has same semantic nature. And if you try to apply it to, let's say, like satellite imagery, everything will be like better idea. So, but experiment shows that pre-trained on something is typically better than like random like Likun uniform or like Glorot or like some other like initializations for weights. There is an example where it doesn't work. In Spring, there was this problem about like satellite imagery, like again image segmentation, but there we had satellite images and they typically come not like in normal as we used to 8-bit format, like from 0 to 255, 3 channels, RGB, like, you know, as we used to. Satellite images come in 11-bit color space, and when we tried we tried like many different things, not just me, like one may think about competitions, Kaggle competitions, some other competitions about human grid search. Many people try different things, the same things, they share ideas, so like it's some kind of reliable, and in many ways more reliable than like results of some paper. So we tried, like me and some other guys, we trying to use pre-trained encoder there on this like 11-bit images, and we're trying to rescale it, like, you know, take this 11-bit, divide by 11-bit, multiply by 255, and some other magic tricks. You apply this pre-trained encoder, same business, doesn't work. Like, I mean, no difference. So in this sense, yes, so, and that's what I mentioned here. So, I mean, if something is pre-trained on 8-bit, most likely images, it will look on 8-bit, like pre-trained on 8-bit, like try to an 11-bit, you may have problems. Question?
Don't you convert this 8-bit to 11-bit just to float?
Yeah, you do this, doesn't work.
Something's wrong. Because you usually add some noise anyway, right? To do.
We all had similar logic, and with similar logic we approach this problem. Doesn't work. Still, data is available. I mean, for this like DSTL challenge that was in Spring, like go ahead and try it, and maybe it will work for you. But yeah, there are some ways to make it work, but they require distribution changes in the color space. And it's again separate story, but like outs of like the box, let's subtract mean, like divide by std or like convert to like RGB, just doesn't work. Distributions are different. It's a rare example, but still happens. Okay, so overall my approach. So when people talk about Kaggle competitions or some other competitions, if you look at the top, they're like basically some crazy ensembling. People like, you know, we had some competition in summer, like, you know, again, no one wanted to do because like very simple problem, kind of Menis type, but on satellite images. But because pipelines was so easy to like to write and we had so many hardware, we trained for 180 networks. And then we like basically made an ensemble out of them. Just because we didn't want to write code and like, you know, just like start something, repeat with different architectures, change few parameters, and then like make an ensemble. And it's definitely the case. Why? Because ensembling is a cheap way, maybe not cheap from computational perspective, you can exchange computational power for better accuracy. And ensembling like definitely works. It doesn't add that like much, but it adds a bit. And so for people that never tried competitions, like common opinion, they're just like, I mean, it's just guys that don't know like actual machine learning, because me and my logistic regression network, we are much better and much more intelligent. And these guys that train like, you know, 100 XG boosts and stack them together, merge it with neural networks, it's all like sucks. But I mean, and it's definitely the case. So I agree with this. But to get to the top, you create ensembles not just from many models, from many strong models. And so here's an example of this. So we had 700 teams. Yeah, I divided my data into 5 folds and trained 5 different networks on every fold, and then I averaged predictions of them. That's what I did. Yeah. So, and in this picture, you can see score on the public and private sets, and also what like place at the leaderboard will it give. Yeah. And as you can see, each of these models independently, like except one of them, will be in top 10 out of 700. Without any post-processing, without any magic, purely you take network, you do predictions, you're in top 10, not top 5, not like top 1, but still, I mean, it's basically a really strong result. Yeah? And of course, yeah, when you average these predictions, you get like slightly better scores. So this kind of a message that, yeah, to get to the top, you need strong predictions, strong models, and this is basically one of them. Yeah, so this is an example of it. So if you hear that someone is saying, these guys, they take extremely weak models, which are much weaker than my logistic regression at work, and then they average them, and then they like win money with this, I mean, be a bit skeptical about it. Question?
So how did you measure the private? I thought that private score is measured only once when you submit the final model. So how did you know your private score on this intermediate model?
Oh, this is actually cheap. Like after competition is over, you still can make submissions. They're not like counted toward any winning or things like this, and that's why like a bit earlier I recommended you, like if you're really interested, download this data set, train your model, and make submission. You still can do it. And if you do it right now, it shows you both your score on the public and on the private. So right now, just go and check. So it's kind of nice resource to check your ideas. Yeah. Next score, what is pseudo-labeling? This is kind of really nice trick because it can be expanded not just from like, competitions, although again, people use it in competitions, but it can be used in production, a real use case. Yeah. So what do you have typically at work? You have, some data is coming, or maybe you can ask for more data, but in terms of labeling, you have, let's say, like, 2,000 images, yeah? And you have another, like million unlabeled. And your model on this 2,000 is not that good, but like, labeling all like million is kind of expensive. What can you do? And this approach, this pseudo-labeling that I'll talk about, sometimes named, okay, when Jeffrey Hinton published paper about knowledge distillation, it was a bit more complex version of this. But yeah, there are ways to get some information from the like labeled data set, and that's what was happening. So when does it work? You need to have a lot of unlabeled data. So let's say if our train set was 5,000, and in this like, unlabeled data set or test it will be, like another 100, it will not show any effect. But because here we have 95,000 like extra unlabeled images, and also this like 5,000 in the tested, because like even now I don't know what was tested, what was unlabeled. I don't have this information. Kaggle doesn't show it to you. It shows you like what you get when you submit on the like public and private part. Yeah. So what did you need to do? So trick is actually like another thing that you need to have. Your model predictions should be relatively high. High really depends on the data set. Sometimes 0.8 is enough. Sometimes like 0.99 is not enough. And what is happening? So what's happening if you like take your train set, training models, predict on some test set, yeah, and there's some mistakes in this test set. Then if you add this test set to your train data, train this again on these bigger data sets with these like noisy labels that you got from your prediction, and repeat this 5 times, you have epic fail. Because I mean, why it's happening? Because network or like some other model will learn this noise that previous iteration generates, and it accumulates and becomes really, really bad. Yeah? But if you do it accurately, and that's what is like happening here, it can improve like your network performance. I believe I started playing with the pseudo labeling probably 2 days before the end, and maybe if I started like not like 2 days but 3, I don't know, something like 5 days, like and again, as like I was working on this problem in the evenings. It may happen that even with my model, without any like folds, anything like this, you could be there like other like participants and like get first place without it. So what's happening? You take again what I've said. You do exactly the same. You train your model. And this model should be like its prediction power should be above some threshold. Then you predict on some unseen data, maybe some test set. Then you look at them and pick those in which network is really, really confident. Yeah. For this case, I believe, I don't remember actual numbers, but I think I picked out of this like 100,000 in the test set, I picked probably 20,000, the most comfortable predictions, and added this to the train set. And what's happening? Like my model was confident there, and because my model is good overall, I kind of trust it. Yeah. And because we added like to the 5,000, we added 20,000, this increase in this data set, even it's like, this like prediction the test set were a bit noisy, it's still a lot. It still adds to this performance. So, I mean, people do it, and yeah, really nice trick. But again, you should be very careful with this, because if your network is not accurate enough and you pick too many of them, you like get model to your data and will accumulate. Yeah.
How do you measure confidence of the network? Is it another regression head?
No, it's actually simple. Okay, so for every pixel that you predict probability from 0 to 1, yeah? Basically, you can count percent of pixels that were predicted from 0.3 to 0.7, and if it's big, network is not confident. If it's on the boundaries, confident. It doesn't mean that it's correct, but it's more about, I don't want like network confidence, network overconfidence. You sort with respect to it, yeah? Question?
You're taking the predictions, you're using them as training. Why do you think that helps? Because those predictions came from the network already, so it's not adding any new information.
Yeah, but I add predictions plus I threshold them. You add some extra domain knowledge into it. So it's not like completely network predictions, but something that's a bit better than this. And again, your network is predicting, you don't pick all images, you pick those that are the most confident, and typically for them network gives like zeros and ones. And also we are talking here about network that we're giving dice 0.997. It's good enough for this case. But again, you should be really careful with this, because error can like accumulate, and network can learn patterns in the error and its own predictions. Yeah? Question?
So you mentioned that this unlabeled test set exists, so you couldn't hand label and just submit, with your hand label data.
You can, but you should be very hardworking.
Right. But this still does not protect from the case where you took some of your test set, hand labeled it, and added to the training set. That's still like a valid thing to do.
Yes, it's a valid thing to do, and most likely some participants did it. I mean, still, there's ways to cheat, but again, if your model is 0.997 accurate, it's pretty hard to label. Another thing, sure, let's say people are labeling, and as I've mentioned in the beginning, we had this mislabeling between different, is there holes in the wheels or not holes in the wheels? I mean, I tried to predict all of them, and I tried to fill all these holes. Score decreases. So in the sense, network learns neural network that was at the head of the labelers, and this kind of helps. So I mean, for this problem, as long as you add a lot of this unlabeled data, it's not a big deal. Another thing, how many masks do you want to label manually out of this 95,000 within 1 week in the evenings?
I just wonder that if you have this model that kind of does really good job at labeling, and you do something like active learning where you only label the stuff where it's unsure about stuff, you can actually get through a lot of this.
A lot is powerful. So yeah, there are definitely ways to do this, and people use it as log. So rules of the games are active learning in this pseudo labeling time regime. If you can basically write some program that goes from some code, some train and test, and does this finds trains the models, does prediction the test, find most confident, throws to train. As long as you can write it as a part of the code, that is totally fine.
Okay, but if you actually hand label, they'll catch you and ban you when, say, you got this person.
No, I mean, so to get money for the competition, you need to provide code that reproduces your solution. And if after the end of the competition you will write some nice model that will mimic your hand labeling, I mean, sure, this works, but I mean, you see there are trade-offs everywhere, and overall, I mean. And another thing, you can hand label a lot of images, and then will be another guy whose model is better, and you will not get into the prizes. And you spend whole week drawing this mask. Cool. So in this sense, it's not really big. Most likely people do this, but I mean, it's not necessarily worth it. Although recently, last year, there were 3 competitions. One with prize $1 million, second $1.2 million, and third one with prize $1 million. There was a lot, I mean, for last one, I know that guy used Photoshop aggressively to increase size of the train set and things like this, because, I mean, and he finished first, because for $500,000, I mean, that you like got in this like couple months of work, it's a good deal. Question?
How do you go from the confidence of a prediction on an individual pixel to whether you keep that a group of pixels?
I mean, so what do you mean? You have like for every like model, for every like, you know, for every image you have on the pixel level, you have predictions of the probability like that this pixel belongs, yeah? And then you can like calculate ratio of the pixels that are predicted between 0.3 and 0.7 to like, you know, like pixels that are like, you know, from close to 0, close something. And this will give you one number for this image. Of course, you can jump to some like, you know, theory of information and this type of the approaches, but I mean, this is good enough and this is like easy to interpret, and we used it, yeah? Okay, next, Alexander's approach. Alexander doesn't have access to like computer with like GTX 1080 Ti's. And you know, he has only GTX 1080. And it's only like 2 layers Ti and maybe not Ti, but for network performance, it's basically 1.5, maybe 2x performance, and which is more important these days when networks become bigger and more like memory consuming. The GTX 1080 Ti has like 11 GB of RAM each, and 1080 has only like, I believe, 7.5 or 8, yeah? And this means that network that like, in my case, this UNet with VGG11 encoder that was able to fit like 1 image per GPU, for him there is no way because he like just like has less memory. So what did he do? He said, okay, VGG is like very consuming in terms of like, it's very consumes a lot of memory. Let's just like change it to something much lighter, ResNet. And he used ResNet 34 that again, Evgeny Nizhbitsky used for some other problem at some point. In this sense, yeah, open data science community is very like helpful resource because people share their solutions at the end and code and things like this. Yeah? So Alexander used this approach and he got some network that consumes significantly less memory and much faster. So for me, I don't remember how much Epoch was taking, I don't know, like 20 minutes or something like this on my network. For him, it was like 2 to 3 minutes on the same input of the images, because ResNet like is significantly lighter, so less computations, and it works better. Yeah? There are some pictures from the paper about skip connections, low memory consumption, but again, like if you Google for LinkNet, and again, I'll share the slides after this, you can like, you know, look for this. It's good architecture. So overall, let's say in the production type environment, if I will need to do like binary segmentation, I will not go for UNet because it's heavy and memory consuming. I will go for LinkNet or something else similar with light architecture that trains faster and helps you to explore more ideas. So yeah, and because for Alexander, even he had less computational like power, but his network was much lighter. So he had 6 models, and each of them trained on 5 folds. For augmentations, he tried horizontal flips, shifts, scaling, rotations, augmentations in the HSV space. And actually, for this competition, he wrote really nice code. So for those that use PyTorch, you know that like in the Torch Vision or whatever library, when you like do augmentation, like, you know, like horizontal flips, like some crop, this like basically 3 types of the augmentations. And if you want something like faster and maybe like bigger and more diverse, you need to write it yourself, and that's what I do. So Alexander, for this competition, wrote really nice code, and on the bottom there is a link, and again, I'll share a presentation, you can go for this. Really nice set of augmentations using OpenCV, and they work really like faster like in PyTorch, and overall like pretty good like set, and many people right now are using like parts of the code that he just copy-pasted from here. Question?
Is it doing it on the fly or he pre-built?
On the fly. So yeah, like rotations, HCV. As a loss function again, like I used BC, binary cross entropy minus logarithm of dice. He used like binary cross entropy plus 1 minus logarithm of dice, still like puts your like network is some, your loss function in some nice range of values, basically doesn't go below 0. As a test time augmentation, he used horizontal flip. What is test time augmentation? Let's say you do predictions of some car, yeah, and it predicts your pixel probabilities. Then let's say you flip this car, you do prediction on this. Again, give you some kind of mask. Yeah? Then you take this some mask, flip one of them, and then you get 2 predictions of the same car that are made in a slightly different manner. Just take average of them, and this basically decreases variance of the predictions, which boosts your score. Again, widely used in competitions and widely used in papers. So if you read some paper, often you can see like some politically correct words, but basically they mean like this. We tried our new and fancy approach. We weren't able to like, you know, overcome like existing state of the art on this data set. That's why we used aggressively taste time augmentation, and now we were able to get like, 1 more % for our model, and now we're state of the art, we are not like everyone else. And I mean, you're like laughing right now, Google, Facebook, like everyone does this because it's straightforward way to decrease variance of your prediction and improve quality of it, yeah? Although requires like twice or like more time of the computation. Next trick that again, like, he was using the optimizer Adam and RMS prop. I don't know which is better because for me they work pretty similar. Again, cyclic learning rate to explore local minimums. He was using Clash for pre-processing, something about histogram matching. I don't really like, remember what exactly it's doing, but some kind of pre-processing trick. Not sure that you need this. Also, he used hard negative mining. Hard negative mining is a nice way to speed up convergence of your models. What is hard negative mining? Let's say you like do training, you do predictions on your train set, yeah? And then for your train set, for like every epoch, for every sample, label and what was the prediction, what was the loss on this example during this epoch. So if you, and let's say for some like epoch, you have like, 10,000 images, and for 9,000 of them, network understands it. It's learned features, it does correct predictions with very high confidence. And for 1,000 of them, basically it makes mistakes. I mean, it doesn't really make sense to retrain it on the whole data set. Let's pick those examples in which network was doing the most mistakes and like train on them. And so you enforce your network, train on something that like makes mistake the most, and basically it speeds up convergence. It doesn't mean that you go to like, some lower minimum, but who knows? But it definitely speeds up convergence. There's extra pain in terms of writing code for this because extra steps should be done, but still. And here are some numbers that show performance of his models on this like data set. Yeah.
Just quick question. What's the point of adding constant to the loss?
To prevent it from being below 0.
Why is that important?
Aesthetics. Okay, Artyom's approach. Again, he used UNet, same architecture as I am. He used 7 folds. He had 2 models. Initialization, pre-trained and not pre-trained. Loss function, weighted binary cross entropy plus 1 minus dice. What's the difference between his loss function and loss function of the Alexander? Typically, when you do segmentation, you can see that like for pixels that are within like your mask, there is no problem. Network doesn't have any problems. But on the boundary, especially when you talk about satellite images and maybe here also, all mistakes typically, if your network like is good enough, you get on the boundary. So of course it makes sense to enforce and to change your loss function so that like mistakes on the like boundaries were more important and it will be penalized like in a bigger way. So kind of like similar to hard negative mining, but like a bit different flavor. And you can incorporate this into your like function, loss function, and that's what he did. Optimize the stochastic gradient descent, cyclic learning rate, of course, augmentations, whole set translation, scaling, rotations, contrast, saturation, converting to grayscale. Reason why he and I used conversion to grayscale, because like in this data set, there was a lot, and you can see this on the streets, white and black cars. And how can you get extra white and black cars? You just like take some red or like blue or something like this, convert to grayscale, you get gray car, good. And so in this sense, it was nice augmentation. Typically, of course, when you're training ImageNet or some other data sets, converting the grayscale doesn't make any sense. But for this particular specific example, based on our domain knowledge, it's definitely like it works. So yeah, he trained 2 networks and like, I mean, numbers are small, but later on you can see this like in this presentation if you look. And he trained 2 of them, one that was initialized from scratch and another like with this pre-trained encoder. Yeah? Which of them performed better? They performed nearly the same, and I would even say the one that performed from scratch performed even like slightly better. What's the difference between them? Initialization is important, it's one thing, but second, I mean, still, because they have different initialization, average is good. How much did it take for him to train? For me, when I used Adam and pre-trained weights, like in total my networks, so on these 5 folds, they have 52 epochs. Why 52? This is a good question. Like probably I was like fine-tuning something after fine-tuning and after some other fine-tuning, adding like few epochs here and there. But for him to get similar results on his like cluster of machines that he like, how to say it like nicely, used without like permission of his like academic advisor on like his university, I believe for each of this, like for non-pre-trained network, it took 250 epochs. So still it converged to the same result, but it took 5 times like more. So yeah, and again, I'm not saying that pre-trained encoder improves your results, but it definitely speeds up convergence in some cases that I described. Okay, what happens after this? Still, I mean, and you need to understand that it's happening within 1 week. Like we started working this problem like 10 days before the end, and we like spending evenings on this. So then we have results, and there is no time or anything like this. We merge our code in some like existing nice pipelines, and it's typically the case for many other competitions. So what do you merge? You merge your predictions. So prediction probabilities for every pixel for all of our like crazy like number of models. Then we took average, and then we looked at the predictions based on the confidence. What's happening? Again, it's very important to do like visual predictions of what you have. And then we look at the test set, and on the top is this guy, white van, that was kind of well known within people that worked on this problem. As I mentioned before, like there was no vans in the train set, to my knowledge, and none of them was definitely white. Same color as the background. So network was confused and tried like to make like, you know, truck out of it and not one. And to overcome things like this, we used convex hull. So we looked for images that are not like very confident. Then we used some kind of traditional machine learning methods to write some like curve surrounding it, and then we were thresholding it. So this is basically it. Yeah, guys, I'll share a presentation. No need to like take pictures, unless you want it. So conclusion. So we finished first out of 735 teams. We got 12,000 in prize. We spent 10 evenings. Okay, I spent 8, guys spent like maybe 12. So on average, it's like 10. Yeah. In total, we used 20 GPUs. And overall, there's like some forum thread on this like Carvana, like, you know, forum near the competition. I mean, you when read how much resources do we have, it's pretty crazy. I believe Andrei Karpathy also has some tweet about this. It's about like, you know, Kagglers don't deserve some money like hardware or things like this. Or our like, you know, machine learning is moving in the wrong directions and something like this, yeah. So basically, there was a lot of 20 GPUs. And another question that someone is asked, if you take all this computational power that people spend like finding this mask, and instead of this, mine Bitcoin, how much will you get? I mean, and this number doesn't look bad because, you know, 735 teams, each has at least 1 GPU, most likely like between 2 and 3. You multiply one by another, spend by 3 months, here and there. This number looks good. Okay, so full reproduction of our training pipeline on one Titan Pascal X will take 90 days. When I mean 90 days, I mean like, you know, all these models, all folds, like for Alexander it was 6 of them, for Artyom 2, for me 1, each of them many folds, things like this. To fully reproduce our inference, you need 13 days on one. Yeah? It's just like, you know, some fun facts. And we never met each other in person. On the right, you can see DevBox, so this machine that I'm using for heavy lifting at my home. So typically I'm using for deploying, but right now, because I was too lazy to write some pipeline, it's definitely mining some cryptocurrencies. At the bottom, there are like 3 links. We also like these things that I talked today in more details and maybe with a bit different angle, you can find at the Kaggle like forum, this Kaggle forum that they invite winners to write the description. We wrote some text there with more details, and yeah, if you're interested, you can go there. We also shared all our code for this competition. If you want to steal some ideas, like copy-paste, like MIT license, whatever makes you happy, and already I believe like, you know, more than 100 stars, like 34, so I have no idea how many. So feel free. I would not say that all of this code is production quality, because I mean, as I mentioned, timeline was tight, and we checked. So here I presented ideas that worked. 10x of them didn't. And we also need to squeeze this, and it's not like full-time thing, but only in the evenings and just like, you know, like writing here and there, checking something. So also, you know, as I mentioned for this like unit modification that I really like here with pre-trained VGG encoder, VGG11 encoder, I released some code. We actually wrote some like, you know, preprint on archive, and yeah, like weights are also available at the GitHub, and I also show some example how to use it there. So again, whatever makes you hope, hopefully it will help you in some way. Yeah, thank you. Questions?
Did you use a batch norm?
I didn't use batch norm. Reason, okay, batch norm is a great thing except all its minuses. In this particular case, batch norm consumes memory. And because issue was here with memory, and because batch was small, basically I excluded batch norm. In some other problems, I used batch norm to speed up convergence, but their images and their resolution was smaller. Or maybe let's just like go with this, yeah.
Any post-processing?
As I've said, we use convex hull to find like, and this, except this, just thresholding, that's it.
Okay.
In this sense, these networks are pretty good. And as I mentioned in like, this network that I trained, this one UNet can get you within top 10 without any prep, post-processing, just purely like fit predict, that's it.
Do we have more questions? There's two that we got on slider.com, and I'd like Vladimir to look into them.
Where can I read more about UNet? About UNet, you can read a lot in the internet. As I've said before, I mean, it's such a popular architecture and so many modifications that you can read like papers, original paper, which is, I mean, implementation is not that good these days because people like, tweaked it and modified a lot. Also, you can open nearly every biomedical imaging like paper about not everyone else and all these things. It will be about UNet. Maybe question can be rephrased, like read about UNet is cute and nice, great, so what? You read about this, some architecture, you remember this, nice name, that's it. Question maybe, how can I get more familiar with using it? I mean, in the easiest way, you take some data, maybe like some open data sets, maybe data sets that you have at work, or maybe some pet project, and try to apply it. Of course, there will be a lot of problems here and there, but I mean, practice makes perfect, you can do with this. If you don't have data set, or maybe you just don't want to deal with this, go to this Carvana, this competition, download the data, it's available, train a model, it's up to you how you do it, train UNet. You can take our code and there's like 10,000 modifications all over the internet, pick any, make predictions, submit to the leaderboard and see how you just like overcome and get prediction that's better than us and everyone else, yeah? So this like the question. But reading, just Google it. What did you learn from your Kaggle teammates? This is a good question. I don't know what to answer. I would like to say some nice words about our teamwork and our like efforts joined together and merged toward our common goal and blah, blah, blah. But not really. As I mentioned, like this problem is extremely straightforward and it's like 10th or like 5th competition about image segmentation this year, maybe like a bit more year than this, that I'm working. So literally for this case, it was copy-paste of the previous pipelines for all of us. And then adding new ideas about cyclic learning rate, HCV augmentation, pseudo-labeling, this type of like tricks and modifications that allow to like enforce you. Of course, like many things that would basically emerge from our discussions. Actually, yeah, like using VGG11 as an encoder, this pre-trained was like idea of the Alexander, but he has some problems implementing this, maybe probably because he didn't have that much like memory in his like GPU, but I was able, and that's why like I was using this, and then like also Artyom. Actually, that's it. It's not always the case. Sometimes competitions are so hardcore and so hard, and people have different domain. Let's say again, this like satellite imagery competition in spring. Some of us has more experience like in satellite imaging, mainly because they like read more papers about it during like the competition. Some had like, so for example, like me and my like, friend, and we finished third, he was more experienced in the satellite imagery, like, type of the problems, and I was more in the deep learning, and this helps us to merge together. So when problem is like hard, diverse, and non-standard, it's definitely the case, it's definitely happening. But this one, we didn't want to participate. Okay? Actually, yeah, there was only 2 questions.
Do we have any more questions from the audience?
Yeah.
Sure.
Hi, yeah, very good presentation. So how you guys divide this price? So one question. The second question, is it easier to make money in a crystal mining than Kaggle competition?
Okay, let's think about this. I mean, of course, again, I can like give you a lot of like beautiful words and some like logic behind them, but let's like speak about numbers. We splitted the price evenly. And again, for me, like living in Silicon Valley, this 4,000, of course, it's money, non-negligible. Like, if you count this in terms of beers, nice amount of beers. But again, for Artyom, he's like, like grad student right now, it's less 2 of his like month salaries. And for Alexander, who's living in St. Petersburg, it's even better. So I mean, just like, yeah, we split it evenly, but effect on our lives is a bit different. Okay, in terms of mining, last year, I believe from different competitions in prizes, I got something like 17,000. I mean, it's better than nothing, but some of like friends, like, Roman Solovyov, well known as like in Kaggle ZF Turbo, he got more than 60 or things like this. So you can do better. So I got 17,000 in the breaks between deep learning when I'm too lazy to write network or like for some other reason, and you start this like mining, I got, I don't know how many, like let's say 5,000, maybe a bit more. So in this sense, competitions are more profitable business, although they require some work. Yeah.
Any more questions? Perfect. Thank you. Thank you, Vladimir, and thank you all for coming.